we did Fourier transforms. And in this class, I don't require you to do a lot of them on the exams and things like that. But I do use it here because it shows what a powerful tool it is and why it really is this very nice change of basis. And we will often talk about K-space and omega space in physics. And the real thing, what you're doing, if we're looking, say, at omega space, is when you Fourier transform a function, in this case a function of time, right, you're going from a function of time to a function of omega. One of the things it's a little subtle that I hadn't really highlighted much. We made the analogy between our Fourier series and our Fourier transform. In the Fourier series, it's real obvious that you're expanding f of x in a basis of sines and cosines or e to the I omega t's. And then you have the coefficients, and you're interested in the coefficients, and they're discrete different coefficients. With Fourier transform, and we call the Fourier series the sum of the coefficients times the basis vectors. Notice in Fourier transform language, we call the Fourier transform what is effectively the coefficients. So the language gets a little bit confusing because I've taken f of t, and how do I find my coefficients in an expansion in omega? I project with e to the minus I omega t, and I get my f tilde of omega. So this was my change of basis to my coefficients. And then I would write f of t as an integral over f tilde of omega e to the I omega t is kind of the equivalent of the series, but we call that the inverse Fourier transform because you're inverting the transition from t to omega by going back to omega to t. So language-wise, this gets called the Fourier transform. And this is the inverse Fourier transform. And if you've noticed, just because it's the most common when you're doing differential equations, I've switched to the convention of my 1 over 2 pi being completely with the Fourier transform instead of a square root of 2 pi in each case. If I'm really thinking carefully in terms of linear vector spaces, I'm going to put the square root of 2 pi in each case because that's my normalization factor. And again, that's part of the confusion of dealing with these. Also, whether the inverse or the Fourier transform itself has the plus or the minus I is a convention. And often you'll see, like I said, when dealing with space, we take e to the minus ikx as our basis and e to the ikx as the projection because of the bra and the Ketz, and you change the names. Yes?
Should the inverse Fourier transform be d?
Yes, it should be d omega. Thank you. Because it's a function of omega. Now, why is this so powerful? Well, if I'm going to consider the Fourier transform of f prime, which is a little tricky to write, what I'm considering is df dt times e to the minus I omega t dt. If I want to compute what that is, what do you think I'm going to do? I told you there's one technique for integration that you need to remember.
Total derivative.
No, that was differential solving.
Oh, answers. You know the answers.
No, that's differential equations. Integration by parts, moving the derivative from here to here. This is very important for those of you who showed up today, because that is an important technique of integration. And you have a test on Friday where you're going to have to do Fourier series and compute coefficients. You might want to keep in mind integration by parts. Just, you see, there's some value to going to class. So if I'm going to integrate by parts, remember I get a term that's on the boundary, but by definition our functions are 0 at plus or minus infinity. I get a negative sign for integrating by parts. I keep my 1 over 2 pi. I have my integral from minus infinity to infinity of f d by dt of e to the minus I omega t dt. So keep in mind that this comes from the by parts. And now I can take the actual derivative, and I'm going to get a plus I omega, because omega is a constant as far as the integral is concerned, 1 over 2 pi, the integral from minus infinity to infinity of f of t e to the minus I omega t dt. Oh, on the outside? Remember, my functions are all chosen so that they go to 0 plus or minus infinity. That's something, because I'm doing physics, I can just not worry about what happens at infinity. Because we're working with functions that are part of our linear vector space, and our linear vector space was defined to be 0 plus or minus infinity, or all of these integrals and stuff aren't defined. Yeah, if you were looking at a more general set of mathematical problems, you'd have to worry about possible problems there. Now, what is this? Fourier transform of f. So I've just got I omega f tilde of omega. And having done that, what would you expect for the Fourier transform of the second derivative? Negative omega squared f tilde of omega, because you're just going to bring down another I omega. So now what I can do is I can take my entire equation and Fourier transform it. And this sort of principle in physics we use a lot, where we do something to an entire differential equation that often involves an integral that works out nicely. Now, by Fourier transforming, what we're going to be able to do is get an exact solution out, because our constants are constants. This could also work even if these were functions of time. If we had constants that depended on time, we can still do the Fourier transform of this. It's still defined, and it still fundamentally changes derivatives into algebraic things. So what we get is minus a omega squared f tilde of omega plus I omega b f tilde of omega plus c f tilde of omega equals 0. Now notice, for this type of equation, nothing much is different than what we had before. Because I can cancel out my f tildes of omega, and I'm going to get an equation for just certain omega that survive. And I get the same result, that in the case when it's equal to 0, there's only 2 omega that really solve the equation. And this doesn't make, this is kind of, by plugging in e to the I omega t, I did my poor man's version of a Fourier transform. And if only 2 frequencies survive, then the Fourier transform of the delta function at 2 frequencies is the e to the I omegas at those 2 frequencies. Something to contemplate in the privacy of your own home. Now, what becomes way more powerful is if I replace this with a driving function g of t. So now if I consider all of the stuff on the left to be some linear operator L, if I am considering L acting on f of t equals g of t, when I do the Fourier transform of both sides, I now get minus a omega squared, all of this stuff, equals the Fourier transform of G. And what that's done for me is I've turned my differential equation into an algebraic equation, and I now know the solution in Fourier space is this. And I can write it as a chi of omega times g tilde of omega, where chi of omega in this case is 1 over c minus a omega squared plus ib omega, and we call that the response function. And we go back now to the beginning of our class where we wrote things like v equals iz, and z was our response function. And we understand now that we can find the phase shifts, amplitude shifts, and changes in the behavior between the driving force and the response of the system. And what's even more amazing is there are many physics experiments that fundamentally work in frequency or k-space, and basically anything that's scattering. So if I have a scattering experiment where I send in light or sound with a particular frequency, and then I get out the reflection or the transmission, I will get a response at that frequency. I will get a phase shift, an amplitude change, and then if I sweep the frequency of my drive and measure the response, I will measure this directly in frequency space. I never have to inverse Fourier transform my equation because I'm working in frequency and k-space. So I can do the whole thing with algebra. Now, if I end up having to work in real space, I just inverse Fourier transform, and I'm back to real space. And now this is the reason why you need to learn complex analysis, because in inverse Fourier transforming this, all sorts of interesting things happen when I have poles or weird behavior in the complex plane. And it's fundamentally, in this particular case, obviously complex because of my eye sitting there. And so this structure is not just a mathematical trick, it actually matches the experimental methods and tools we use a lot of times when we do physics. Any questions on that? Now keep in mind this, if I did it with plugging in my e to the I omega t's, I could do it with this and get a particular solution and then add that to my homogeneous solution. Did you have a question or? No. Okay, thought you did.
Oh, so is the z pointing towards the whole chi or just the imaginary?
So in this case, z is the whole chi, right? In this, when we wrote down v equals iz, okay, it was not quite this. Actually, 1 over z would be your chi, because v is usually your driving and I is usually what your response is, so you put the z over here. Okay, so it's not quite the same, but it's the same basic idea. Right? V equals iz came from the differential equation for a circuit, Fourier transformed, basically, is how you got that. And that's actually a problem I'll give you to go through at a later date. Any questions on that? One other comment, now you can see why we did our manipulation with complex numbers, because what are you going to do to this? You're going to turn it into a phase and an amplitude. You would really like to write this instead of this as r e to the I phi. And I leave that as an exercise to you to go practice your complex number manipulation to turn it from this form to r e to the I phi.